Hey statisticians, we're going to look today at what happens to a set of data and what happens specifically to the summary statistics in a set of data if we decide that we're going to take our data and maybe multiply by a constant. So that would happen if you were going to change units, for example. You might have to multiply or divide everything in the list by a specific number. We're also going to look at what happens if we add or subtract the same value to everything in the list. So what I've done is I've created this histogram on this list L. I just made up some numbers for this list and created that histogram. So here's the histogram for list L. And then I want to look at what happens if I take this histogram L and I add a constant to everything in the list. So here I've added nothing. So the histograms overlap one another. So you can kind of see if I turn this off. So the blue one is the one where I'm adding the constant. So if I slide this around, this would be adding 15 to everything in the list. So you can kind of see what happens to the new histogram compared to the old one as I add values to the list. So I add 15, add 30, and then add another 15. So now I'm adding 45. And hopefully you can see that what's happening here is that the histogram is literally just shifting back and forth. So what you should notice is that the spread of that histogram is not changing. It's not becoming more spread out. It's literally just shifting back and forth. So in terms of transformations, adding a constant is really just a translation. So if you think back to geometry, a translation was just moving a shape back and forth and moving it around. So that's what's happening with this. As I add a constant to everything in the list, what's happening to the distribution is it's just shifting back and forth. And it's shifting the same amount that I've added. So here, if I subtract 30 from everything in the list, everything here is 30 less than it was before. So I've just taken that whole histogram and shifted it back 30. And then if we take everything in the list, and now we're going to multiply by a constant. So now this one's sort of purple. So right now, B is 1. So that means I'm getting the same histogram that I had before because I've just taken everything in the list and multiplied it by 1. So I haven't really done anything yet. But if I slide this around and start multiplying by 1.5, now you can kind of see not only is it shifting in this direction, but it's actually also getting more spread out. So our minimum now is from about 200 to almost 430. So this is getting way more spread out than it was before. I think it's probably ended up going off the screen, but you can kind of see again, as I multiply by a constant, what's happening to the distribution is it's getting moved away from the origin, but more importantly, it's getting more spread out. Whereas when I added a constant, it didn't get more spread out, it just shifted back and forth. So this one is shifting, but it's also spreading out. And then if I multiply by something less than 1, what's going to happen is it's going to get more compact. So down to 0. So here, now this is less spread out than it was before, and it's kind of getting pulled back towards that origin. So the key to notice there is when I multiply by a constant, the spread is also changing. So our our center is changing, and so is our spread. So let's look at summarizing what we just saw in that demonstration. So when we're shifting or scaling, right? Shifting is when you add or subtract a constant to every value in the list. So when we say adding a constant, if you add a negative, that's the same as subtracting. So we're just going to say adding a constant, but know that that constant could be negative. So the effect that that has here, as we just saw, is that it translates the distribution just back and forth. And it translates the distribution a distance of whatever you added. So if you added 10, it's going to translate up 10. If you subtract 5, it's going to translate back 5. So what's happening here is all measures of position, so anything that's measuring center or the quartiles, those are going to increase or decrease by that same constant. But measures of spread don't change because, again, the whole histogram is just shifting back and forth. It is not any more spread out than it was before. So if you're shifting or scaling, things like the standard deviation and the IQR and the range, those are all going to stay constant, even though you've changed the values in the list. So think back to that histogram sliding back and forth when you're trying to decide how things are affected. And then for scaling, now we're multiplying each value by a constant. And the effect that this is going to have is it dilates the distribution horizontally. So as we saw again in that demo, as I multiplied by something bigger than 1, the distribution got more and more spread out. And in this case, the measures of position are going to change, and they're going to get multiplied by that same constant. And the measures of spread will do the same thing. So if you're scaling a data set, then everything changes. So if you multiply everything in your list by 3, then all measures of position are going to get multiplied by 3, and all measures of spread are going to get multiplied by 3. So let's take a look at an example. So let's say that these are the summary statistics for a 40-point quiz. And then we want to look at, let's say I want to curve it, and I'm just going to add 10 points to everything. What impact will that have on each of these? So you want to think about whether it's shifting or scaling, and then I would strongly recommend that you take each of these summary statistics and you identify them as a measure of spread or a measure of position. So I typically will label them, and if it's a measure of spread, I'll put an S next to it, and if it's a measure of position, I'll put a P next to it. So that's what these will look like. So the only measures of spread in this list are IQR and standard deviation. Range would be the other measure of spread. So for this case, right, the shifting here, if I'm adding 10, remember the spread doesn't change, I'm just shifting everything up 10. So the IQR and the standard deviation are going to stay at 8 and 6, but the rest of these are going to have 10 added to them. So this is what we'll end up with if we took that same list of quiz scores and added 10 to everything in the list to get quiz scores out of 50 instead. These would be the new summary statistics. So right now, pause the video for a second. See if you can fill in the table for what would happen if we doubled every value and made the quiz out of 80 points. And then if we wanted to make the quiz out of 100 points, one thing I could do is I could double every value and then add 20. And that would get me a 100-point quiz. So pause the video, see if you can fill in the values for those summary statistics if we double everything in the list, or if we double everything in the list and then add 20. So for doubling, this is a scaling, right? We're going to multiply everything by 2. So this is the one where it's essentially a dilation in terms of geometry terms. That transformation would be a dilation. So everything's going to change in this case. So every one of these is going to get doubled. And then for the last column, we're going to double everything and add 20. So here's a case where you want to think about order of operations. And the order of operations here follow what they do normally. So you'd multiply first and then add 20. So the first thing that's going to happen is that scaling right here. And that scaling we already did. That's this column right here. And then the plus 20 is a shift. So everything, again, everything's going to get multiplied by 2, but the only things that are going to get 20 added to them are measures of position. So all the things that are listed over here as a measure of position will get doubled and add 20. But measures of spread are just going to get doubled. So that column should look like this. So here I'm just taking everything from here and adding 20, except the things that are measures of spread. So the IQR and the standard deviation, those are going to stay at 16 and 12. All right, so next up is what would we use standard deviation for? So here's an example where, let's say that we've got a decathlon that's happening, and all the competitors were tied after the first 7 events. So these 3 guys were tied after the first, not all the competitors, but these three competitors were tied after the first 7 events. And here are the results of the last 3 events. So what I want you to do right now is, it's your job to figure out who should get the gold medal, who should get the silver medal, and who should get the bronze medals, right? So who's getting first, second, third place overall. So we're going to assume, again, that they tied in the first 7 events. So it really comes down to, or that they were tied in total points after that. So it comes down to these last 3 events. Who should get the gold medal? Who should get the bronze medal? Who should get the silver medal, right? So go ahead and think about it for a minute. Think about what, if you can answer that question, and then we'll see if you maybe need more information. So you've probably realized, I think, that, this example was set up intentionally to really not be able to be answered just yet. Because if you look, you'll notice that for each event, competitor A finished first in the shot put, last in the long jump, and second here. So we've got a first, second, third, or first, second, third, and then same thing's going to happen with B and C, right? Each of them finished first, second, and third in one of the events. So that doesn't help us now, right? We still can't determine who should get the gold medal. So some information that might be useful is if we knew the mean and standard deviation for all the competitors overall. So if we take all the competitors and we find the mean and standard deviation for all of them, we can now, this is very, very useful information. Because one thing that's happening here is that you're trying to compare an event that's measured in seconds to an event that's measured in feet, in feet and inches. And really, you can't. There's no way we can compare those directly. So what we can do though is we can look at how each competitor did in their event relative to everybody else. So again, pause the video right now with this additional information and see if now you can determine who should get the gold medal, who should get the silver medal, who should get the bronze medal. And then think about who had the most outstanding performance overall of these three competitors in these three events. All right, so here's what we just did. Hopefully you came up with something like this. So what I've done here is I've figured out first how far each competitor was from average. So for the first one, right, 10.1 seconds is 0.1 second off from the average. And then what I'm going to do here is I'm going to use this measure of spread. Because remember, the standard deviation is sort of like the typical distance each competitor is from average. So we can kind of use that as a ruler to see really kind of, relatively speaking, how far is 0.1 seconds away from average. So I'm going to divide that 0.1 seconds, divide by 0.2, and I'm going to get this positive 0.5. And I did that for all of the competitors here for the 100-meter dash. So here, this competitor was negative, was a half a standard deviation below average. Here, this competitor was a half a standard deviation above average. And then this competitor C was actually 1.5 standard deviations above average. So one thing to keep in mind here, that for 100-meter dash times, being above average is actually worse because that means you were slower. So that's something to keep in mind, that we may want to, in this case, sort of think of this instead of it being positive 1.5. We kind of want to think of this as being a negative 1.5 because it's 1.5 standard deviations worse than average. And the same thing here. This is really going to be a plus 0.5, and this will really be a minus 0.5 to reflect the fact that faster, that higher times are actually worse. And then for the other competitors, I did the same thing for the, so we did the same thing for the other competitors in the other events. So here, again, I'm comparing each one to the average, and then using this standard deviation as my sort of typical distance from the average for everybody, and using that to figure out how many standard deviations away from average was each of the competitors in that event. And again, I did this for each of the events for each of the competitors. So it's really important to note here, think about what the units are on each of these. So if you think about just this calculation right here, when I did the 10.1, I get 0.1 seconds, right? That was that difference in the top, divided by 0.2 seconds. So the top difference is in seconds, the bottom is in seconds. So these actually cancel each other out. So this value right here, the number of standard deviations away from average that this competitor is, doesn't have any units on it. None of these, all the units on these cancel. In this case, right, the difference in the top would be feet, the bottom is 3 feet, so those feet cancel out, and you end up with something that's unitless, which makes that value very, very powerful, because I went from things that had different units on them. These didn't. I guess I could have combined those, but I can't add together seconds and feet. But I can add these together because these don't have any units on them anymore. So now if I total these up, this one comes out to be a positive 1.5, competitor B comes out to be 2.5, and competitor C comes out to be 3.5 comes out to be 2. And now we can use these to determine who's going to get which medal. So based on this, I would say we get gold, silver, bronze. And you might be able to make the argument maybe that competitor C did extremely well relative to everyone else in the long jump. So for the long jump here, this is the most outstanding performance for these three competitors for these three events. So you may want to make the argument that competitor C should get the gold medal, but competitor C also did pretty crappy over here relative to everyone else in the 100-meter dash. So what these things are called, and you may have heard this, but each of these things is what's known as a z-score. And a z-score is going to be something that we're going to use a lot. And what it will allow us to do, again, it gives us an idea of where someone stands or where an individual is relative to everybody else. And the formula for z-score is the average minus the mean divided by the standard deviation. And what it's really getting for you is how many standard deviations above or below average is that individual. So again, here, competitor A here was 2 standard deviations better than the average competitor in the shot put. And because they're unitless, they're very, very powerful and allow us to compare things that we wouldn't normally be able to compare, right? So your whole life you were told you can't compare apples and oranges. It turns out that if you use z-scores, you actually can compare apples and oranges, just like we can compare seconds and feet by changing to z-scores.